Hello teacher, I'm Enes Canbulat. Today I'm going to show you my Java homework 4 and let's start. Firstly, take a pencil and let's start with first question. When we look at this function, it visits each element of the input array exactly once. It checks whether the element is negative, and if it is, it squares to do sum. These checks and the addition operation are performed in constant time like O1. Consequently, as the array size n increases, the execution time grows linearly, and therefore the time complexity of the function is expressed as an On. When I look at the second question, and let's start with the left side. Uh, sorry, left side. When we analyzes the first question, the loops runs from 0 to n square, and n multiple n is n square, incrementing by 1. It's the number of iterations is n square, and time complexity is O n square. When we look at the second question, the loop still goes up to n square, but in steps of 40, and its number of iteration is n square divided by 40. It's still proportional of n square, so time complexity is O n square. When I look at the third question, it's incrementals e by n each time, and iteration count is n square divided by n is equal to n, so the time complexity is O n. When I look at this question, the loop goes from e equal to 10 to up to n square divided by 3 in increments of 2. So roughly our time compressions is n square divided by 3 divided by 2. It's equal to n square, like this, n square divided by 6. It's again still proportional of n square, so time complexity is O n square in there. When we analyzes this code, this loop always runs 1 billion, a constant independent of n. We don't have any n in there, so time complexity is O1. When we look at the right side, when we look at there, each iteration multiplies e by 2, and starting at 1 and going up to n. You can do this about logarithm 2n times before e reaches to exits n. So our time complexity is O logarithm n. When we look at the second question in right side, the loop as written is a bit unusual, because if our n is bigger than 10, the condition is e lower than 10 is false right way, so the loop never runs. So That is effectively O1 time because it does 0 iterations. But if n lower than 10, uh, e lower than 10 is true initially, so it enters the loop. However, dividing by 4 repeatedly can quickly take e down to 0 in integer arithmetic, at which point e lower than 10 stays true forever. This would be an infinitive loop, so it's potential infinitive loop. After that, when we look at the third questions of the right side, uh, the outer loop is this. The outer loop is roughly n divided 100 iterations, so O n. The inner loop is down to 40 in steps of 4, and that's about m and divided by 4, and its iterations of OM. When we calculated this, two loops are nested, so the total work is O n multiplied by O m, and it's equal to O and multiplied by m. Okay, uh, for 4 questions in right side, the outer loop is multiplies e by 5 each time. So it runs about logarithm 5 n times. So it's O logarithm n in there. The inner loop goes from g m divided 2 to g lower than m. So it performs about m divided 2 iterations to OM. Nested together, the total is OM multiplied by O logarithm n. So it's equal to O m logarithm n. And this was second question. And when we look at the third questions, what is the time complexity of the following power function? This is a classic exponentiation by squaring algorithm. At each step, the exponent n is effectively halved by divided 2. Consequently, the recursion of depth is proportional to logarithmic n. So making the time complexity is O logarithmic n easily. In the fourth question, what is the time complexity of the following Fibonacci function? We have Fibonacci function in there, in this function. This is the classic naive recursive implementation by Fibonacci, which recomputes many values repeatedly. Its time complexity grows exponentially with n. More precisely, it can be shown that the runtime is on order of like O n, where O n similar to 1.6018 is the golden ratio. In Bitcoin notation, we often simplify to O n power of 2, and that was the fourth question. We have interesting fifth questions in there. We have faster computer or algorithm questions. We have problem with two different solutions, and we have two algorithm and two computer in there. We have faster computer. Its time complexity is like 0.1. It's 10 times faster than a slow computer. So when we multiply 10 with 0.1, it's equal to 1. It's the time complexity of our slow computer. After that, we have a slow algorithm in there. A slow algorithm takes O 2 power of n time, and fast algorithm takes O n time in there. Slow algorithm running on fast computer, meaning we have slow algorithm in O. Okay, we don't have to write O in there. N square multiplied by, because of fast computer, 0.1. And when we have fast algorithm running on slow computer, we have slow computer one time complexity, and fast algorithm has n. So we have n multiplied by 1 equality in there. We have a two algorithm in there. So when we write a 10 value of n, it's equal to 100 multiplied by 0.1, and it's equal to 10. And when we tend to this algorithm, it's 10 multiplied by 1 is equal to 10. It's our location, 10 location. And when we have to values lower than 10, when we have to lower values than 10, like 9, we have to calculate 9. We have 81 multiplied by 0.1 and like 8.1 in slow algorithm running on fast computer, and fast algorithm running on slow computer, when we calculate, it's 9. 9 is bigger than 8.1. It shows us to when we have a lower value than 10, it's slow algorithm running on fast computer is more faster than fast algorithm running on slow computer. But when we have to bigger than 10 values, our fast algorithms running on slow computer faster than slow algorithm running on fast computer. So it was my homework, teacher. Thank you for listening. See you.